pull that up and just have it open. Okay, so then if you go on further, what can you tell me as far as temperature related to these? Or related to the collisions, per se? What were you going to say?
I was just saying, it's kind of confusing because there's like a certain number of blanks and I don't know what specifically he wants me to say.
Okay, so from those, I wasn't exactly sure. Some of them, as far as his specific blanks, it was just like, I just wrote down the general concept that we were discussing and started saying, screw it with the blanks.
I
So
put at room 10 with a question mark, but I don't think that that's right, but that fits the 3 blanks.
let's see if I can open this larger. So that would not be fitting for that. Like I said, I don't know what your exact 3 blanks are, but when we're discussing that the temperature is far higher than the boiling temp, that's what we're discussing as far as just this energy. Really the concept that at a very high temperature, these particles are moving so fast and they're moving just kind of really chaotically everywhere that we're not seeing really any energy lost in a collision. So it's such a small fraction of the overall kinetic energy between all of these particles that that's not making an impact. Like I said, I don't know what specifically your 3 blanks are. If it's I just put far from boiling. That's the best I had for 3 blanks. But does that make sense, that concept in general? Okay. So another thing to kind of understand on a higher level with that is that when we're moving from a solid structure to a liquid structure, we're going to see more of our entropy increase because entropy is a higher, we're looking at the higher rate of disorder. And so when your energy changes when you're in a gas phase is going to be far less noticeable just because you're in a very high kind of state of disorder, and so any sort of temperature change in that isn't really going to drastically impact that high rate of disorder again. So the higher you are, the less energy change you notice, as long as you stay within that state. What?
The higher temperature?
Yeah. Yeah, sorry, that piece is crucial. And okay, and then what can you tell me about B on that portion? Or do you guys understand that? I guess going down, do you want me to continue down this page, or do you guys just want to kind of jump to very specific things?
Can we do B?
Yeah.
Do B? That one I did not get at all. The density is blank.
Okay, so the average distance between the molecules is, I didn't write down the blanks to answer this, but basically your average distance is greater. So when you're working in a very solid structure, you're highly ordered, you're all tightly compacted, and you're staying in your same spot, that's when you would notice more of an interaction. And then in a liquid, the particles are moving slower, and so in general, they're not moving as fast, and they're kind of you would see more of an interaction there. Whereas in the gas phase, you're moving so fast, at that point, although you may come into contact with each other, you're constantly moving so fast that your distance is farther apart. And then I don't know what the compared to the blank of a molecule. Oh, compared to the size of a molecule, probably.
Wait, what was it? Sorry.
So, no, you're good. So, with an ideal gas, the concept of like the no volume, this is kind of going through to explain why there is considered no volume, is that you have a lower density or a lower pressure. And so the size of a molecule is technically like negligible or in a way like irrelevant compared to your like average distance between the molecules. So it's probably density is low, so the average distance between molecules is negligible compared to the size of a molecule.
Seems fitting to me.
That's what I think too now. Okay, and then what can you guys tell me as far as your 4 laws of dynamics? Or thermodynamics?
The four laws.
Yes.
The 0th one is like when A and B are in thermal equilibrium, and B is in thermal equilibrium with C. That means A has to be in physical equilibrium with C.
Yes. What about the first law?
Conservation of energy. Energy can't be created or destroyed.
Okay, and then how would you like note that internal energy equation?
Like the Q minus W,
Yes, and what is that equal to?
the delta internal energy.
Yes. And then,
What was that equation?
so it's delta U equals Q minus W. And then the second law.
I found kind of 2 different things, and I don't know.
There
if
are
they're
2
both-
different things.
Okay. The first one I found was that heat transfer occurs spontaneously from high to low, and then from high temperature to low temperature, and then also that like I think it's like with heat engines, or like something that can't be 100% efficient or something like that.
So kind of going off of that, so in any like natural process, your entropy will increase as your energy transfers from a higher to a lower like temperature. And then the second aspect is that with the heat engine, they're converting their thermal energy or heat into mechanical energy or work, and that aspect there can't be 100% efficiency.
Wait, did you say when it goes from high to low, it increases the entropy?
Yes. It will naturally just do that.
And then the engine is not 100%.
Yes.
Not 100% what?
Not 100% efficiency.
And it's going from.
And then the temperature is going from high to low. So like if I have like I naturally run very warm. If I touch you and your hands are really cold, my heat is going to transfer to you rather than your cold transferring to me.
Okay, but sorry. The 100% efficiency is due to the work of a like you're getting mechanical work.
So you're getting, you're converting thermal energy into mechanical energy. Thermal energy being your heat and mechanical energy being your work. They're like synonymous terms at that point. And then, what is your third law?
When temperature reaches absolute zero, entropy is zero. That sounds all right.
Yeah, and really just the biggest piece is that nothing can reach a temperature of absolute zero.
Nothing can reach one.
Yeah. Okay, so what can you tell me about your heat pump or your heat engine versus your heat pump?
Heat engine converts heat to mechanical
You got it.
energy, and then the pump, it can take like heat out of a system or put heat into a system, right?
So the biggest thing is really your heat engine is correct. Your heat pump really just does the reverse of it. So you're gonna put work in to get heat. And then let me see where we're back at on the paper. I jumped a little bit. So number 4, once again, I didn't really know the size or like your 3 blanks there, but temperature is going to, I mean, it's kind of proportional to a lot of things. It's going to be, like, it works in a relationship with pressure as you're determining, like, your phase changes and whatnot, but it's also, like, proportional to the size of an object or the amount of an object, so you have to take your mass into consideration when you're looking at temperature changes and how much energy needs to go into changing a temperature. So once again, I didn't know your blanks just because I didn't know what specifically he wanted there, but it's kind of proportional to a couple things.
I was thinking it was proportional to the average kinetic energy of the molecules.
That would also be true. And do you guys understand how, with entropy, how to calculate your microstates and your macrostates?
No.
Okay.
Not at all.
I did a dice example. I want to say that that's what he did too. It's just easiest to use a dice example just to make it very straightforward and clear. So we can go through that. If you guys want, we can go through that now, or we can go through that as we get through farther through the page. I don't really care.
Can we go over the 4 variables of state? I don't know.
Is that just pressure, volume, temperature, and number of molecules?
Let me get back to my
That's what I
sheet.
put. I looked it up on the good old interwebs.
What was it?
Pressure,
Yeah.
volume, temperature, and then the last one, D, is number of molecules. Pressure, volume.
And that's really just looking at
It's
your
looking at
equation.
The PV equals nRT.
Mm-hmm.
Pressure, volume, number of molecules, and then temperature, because your R is a constant. Those are the 4 variables.
It's really just saying that when you're looking at like an ideal gas, those are the 4 different aspects that you can sit there and play around with and change in order to, change anything. So, like for example, on that, when we get down to it lower, we'll look at our critical point, or like the critical temp. It's basically saying that above that temperature, a liquid cannot exist. And so that's kind of saying that we're looking at the fact that temperature and pressure are going to kind of dictate how we're going to change our phases and whatnot pretty closely. And so sometimes you can have, like, at a higher pressure, you'll have to reach a higher temp before you'll reach boiling and then go to the gas phase. So that's why we look at, like, different geographic regions. Cooking is a little bit different because you have to take that into account. So there was an example in the book where, like, when the pressure was somewhere around like 300 or something, you had to, or 218, I want to say 218 atmospheric pressure. Your boiling point was no longer like that typical 212 Fahrenheit. It was like 300 and something degrees. So as you're looking at that, there are some different like materials that no matter what pressure you go up to, you still can't reach or you still can't maintain a liquid above that temp. It's very a word vomity way of saying that. So what's your equation for an ideal gas? Andrew had it earlier, so someone else give it to me. Okay. And then...
Me too. And this is one of the gas. This is like the easiest part of the gas.
How did that go?
Oh, well.
Good. Okay, so with the critical point, go over that again. Above a certain critical temp, a liquid cannot exist. So basically with this, the gas will have the density of the liquid, but it won't be able to condense into that liquid state. And then your triple point, does anyone know what that is?
It's where all three of the phases exist.
Have you seen it?
Yes.
No. I'm not
If you have it in a thing and then it's ice boiling
I love things like honestly, one of my favorite. I'm not joking about that. I get really excited when I see them.
Just one of those things, it's fun.
I have a question.
Yeah.
So working on this worksheet, problem number 2, there's the velocity, VRMS, what is that called?
So that's your average velocity. It's really just like the average velocity of the particle. I can't remember what the RMS actually stands for.
What's the difference between the little m and the big M?
So,
Isn't big M molarity?
yes,
and then
but
molality.
Physics.
which specific equation are you looking at? Because there are different.
At the VRMS, you can do the square root of 3kVt over the little m. Do you want me to bring it up to you?
Yes, if I can't get there faster.
Okay.
Amen.
This little guy right there.
Can you point it to mine?
First thing I do is I have this right next to me, so I can
I don't know why you gives all these. Give me a headache. I definitely have one. Just read. I said it was hard stuff. I read it and then I'll get to this. It gave me a 5
Okay, so your big M is your like mass of your mole, whereas the little m is your mass as far as like for your particle. More so because like when you would typically calculate for your mass in like one of the equations using like your 1/3 nmv², you would use your mass and then you would actually have to divide that by, you'd find your molar mass and then divide that by Avogadro's number.
Wait,
Oh, yeah,
for capital M?
So for little m, it would be your, your little m equals molar mass over Avogadro's number. And then big M is the mass of your mole.
So the big M is just like your grams?
Yes. And I'll double check that just to make sure that I didn't say that wrong.
Yeah, so in problem number 2, you're right, because for problem number 2, you take this
Which problem number 2 are you talking about?
on the worksheet.
Oh, okay. I was like, I have no idea what you're talking about
It
right now.
takes the mole, of helium, just 4.002602 grams per mole. That's what you just got with your
Mm-hmm.
Yes. And then you divide that by Avogadro's number. And then you get that number.
So what is the M one more time, sorry?
So little m is your molar mass over Avogadro's number.
And then the big M is just the mass, the molar mass, right?
Yeah, so that's your molar mass. And then if you look at,
Helium, it would just be the 4.
yeah. So if you look at your equations, if you guys each have those, on gas laws for monatomic ideal gases, on the left column, your middle one, it shows your M equals big M over Avogadro's number, or number of particles.
Where is it?
So,
To the left, to the middle. Go to
And
gas
here.
laws of monatomic. Bottom.
so it's this one. So it shows your big M equals mass of the mole,
Oh,
and
okay.
little m, and how to get there, and how to
Okay.
convert between. Did you see that? Or did you
I
guys
did not see that ever.
I have a question for you.
Okay. So that's where that's at when you pull up your equations. So little m being the mass like of the particle, and this is your molar mass, the big M. So what you would pull from the periodic table, and then dividing by Avogadro's number to get little m. Big M, mass of the mole, or molar mass off the periodic table over Avogadro's number to get little m.
Actually, I'm going to trade you. Here's one. You can have it.
Oh, perfect. Thank you. I have it pulled up on my computer, but for some odd reason, it takes so long to look at this. It's it's great that he gives you guys all of these equations, but it's a lot to look
We
at.
should just cut out the one we don't need.
Yeah,
That makes it like maybe not.
It would narrow it down, so maybe it would make it easier per se, but sometimes there are points when
People use different methods.
you can use different methods, or say you forgot whatever this 1/3, if you had to derive it, the 3/2 PV over 3/2 NKT kind of thing, you could literally go back and pull up from work energy equations and pull your kinetic energy equals 1/2 mv squared, and then work with another equation to derive yourself there. So it's kind of nice. It would take you forever, but yeah.
I hope when he does the test on his phone, he multiplies it by at least 3. Like time it takes him. It takes him 10, 15 minutes. That takes a little bit longer.
I didn't like how he couldn't even solve that one problem on our last test. The airplane.
Yeah, when I heard about that, I
He
felt
can't
really
solve it, but he
bad.
does solve it.
I was telling people at work that they don't do physics. And my boss was like, that seems really stupid. I was like,
Like, if you need a spreadsheet, you need to give us the spreadsheet.
Ooh, spreadsheets, I love spreadsheets.
Okay.
Can we
Back
do
to
the
this.
conceptual questions for 15? We don't have to do
Yes.
number 1 because we already did that. But really just number 3 is all I'm asking for.
Cork.
Okay, so. Okay, so. Does anyone have a guess as far as what U equals?
I said n times 1/2 mv squared, or 3/2 nkt.
So I have 3/2 nRT. And then noting that when you have your gamma, it's the 5/3. Let me see if I can find anything else where it's derived.
It's times 3. Wait, no.
Is it 5/3 or 5/2?
What?
Is it 5/3 or 5/2? Like 5/2.
5/3 is what I have.
Because I thought it was like 3/2 plus nRT, and then, or 3/2 nRT plus nRT, and then that's where you get the 5/2. I could be extremely wrong.
The equation right here says like 3 halves nRT or 3 halves PV or 3 halves.
So I have the 3/2 PV equals 3/2 NKT, but then I also have the 3/2 nRT. So U equals 3/2 nRT, and then your gamma is 5/3.
What does that mean?
So sometimes you have like your gamma, like an equation to the power of gamma. I did not include one of those problems because I didn't get that far to including one of those for you guys.
I've never heard of that.
Yeah, me either.
Yeah.
I could find a problem that utilizes that tonight and just like work it out and send a picture.
I think he might have mentioned it, but I don't think he had.
I feel like I didn't see many problems in your guys' homework or the supplemental homework that did that. So I don't know how much you need to know about it. Trying to think.
I've already had about 10 emotional My mom cuts in this much.
Yeah, we can come back to that aspect. Let me make a note for that one.
A little bit.
Okay. Did you guys have your 6 or your 5 and 6 figured out?
I do.
No.
Okay.
If you go to the OneNote, he did this huge little box.
Where is his OneNote stuff at? Because I tried to find the OneNote review.
You gotta go to Moodle.
No, and then it's with all the links. It has like the little chainy thingy on it.
There's a link to it.
Okay.
You're talking about what he did today in class?
No, so in the chapter 15 OneNote, there's a
See if I can
box
get there.
and you put all of it there. So the answers
Like
to
way too many tabs open right
5
now.
and 6.
Girl, same.
Okay.
All the time.
It's so
So
bad.
if you just look there, he has like, if it's isochloric or choric, how do you spell that? Is it isochoric? Chloric.
Isochoric.
Choric.
Yeah.
I've been calling it isochoric because it just makes more sense.
I think it's
Um,
isochoric.
He has work, the like equation for work, energy, and something else. He has like 3.
Wait, what? Oh no, yeah, keep going. This one.
Oh.
Didn't he say we didn't need to know how to? Because like
I've
that's
never
all
looked
part
at
of
this.
the like.
And so it has all of it, and then it's the
either
worksheet.
backlog. It
Okay.
said
Notes
that's
from
all we
his
need to know is
lectures,
that
and that's the worksheet
PV equals nRT.
that pops up.
4 or 5.
And you
and 6.
scroll down, I guess.
Yeah, because like
He uses all of those equations in the very long problem.
Okay.
15.
Yes. And I just finished that, and there was some stuff, like, it makes sense when you're doing it. It's very much the same thing over and over again. But there was, for state C, for number 2, he does this 2/3 thing. I'm guessing it relates to this up here. I gave up a lot of time on YouTube at that point. Different kind of YouTube video. I had to get my mind off of it.
Man, I wish I had known about this like OneNote link ages ago. Okay.
So my question is number 3, but we already figured out 4. For a diatomic ideal gas, the change in internal energy is given by, and then it says at low temperatures, the change in U.
What does U stand for?
Work. Right?
U is internal energy.
Sorry, internal energy.
I think you have to go to work.
Yeah, have fun.
Maybe.
Okay. 4, I did not get to because I was looking through there and I couldn't find it in the text right away. So I skipped on and went to 6, and 5 is basically 6, but you just have to manipulate the equation.
And he has that all in his.
He what?
He has that on his window.
Oh, he has 6 on there filled out?
Well, not really 6 filled out, but like there's, if you kind of scroll down into the side, there's like this box, and it's like.
Oh, perfect.
And it can give you all the answers.
Okay, yeah. Well, I filled out.
What I kind of learned from doing these is that it just helps you realize where to look at the equation sheet when you're doing it.
Which is helpful because that's the biggest piece to be able to, you have to understand how to utilize your equation sheet to be able to, manipulate those. But I can continue looking through the text for 4. I couldn't remember all of the details of that. And so I just skipped that one and went on and just didn't have time to go back to it.
Okay, that's all my questions. Anything else, Grant?
Do you guys understand 5 and 6 of chapter 15? And then I have problems still for us.
You mean problems 5 and 6 or?
So, of the conceptual stuff.
Okay.
I hate this.
It's very long.
Oh my gosh.
I know I saw that. Does he expect us to do this in 45 minutes of
My guess is that this might be a synthesis question, where you only have to go from base A to B, maybe 3 spaces.
Damn it. Okay.
And that kind of thing. But
So, we'll start with the entropy concept, and I'll just do it on this, and I'll pull this down. Okay, if we're looking at 2 dice, what can you tell me about the macrostates? Or what can you tell me about macrostates in general?
Where's these macrostates coming from?
So this is dealing with entropy. And when we're looking at entropy, we're discussing the fact that, when you're looking at your equation, the omega is your number of microstates in a macrostate. So your macrostates are your combination of PV, N, and T. And then it's one of those things that it's really kind of confusing as far as the terminology of it. But just looking at just a straight up example helps to kind of better explain that. And so then a microstate is considered your number of both position and momentum, like arrangements for a molecule within the macro state. It's one of those things that honestly, trying to determine your omega there is just a pain in the butt. And so this is like the easiest example to kind of just make it a very straightforward thing. So when we're looking at our entropy equation, what does anyone know which equation to use with the omega? Okay. So we're looking at for entropy defined as S equals constant K times the natural log of omega. And what is your constant K equal to in this case? What?
Is that what you're looking for, 8.314?
No.
You're looking for a number or,
I'm looking for a number.
okay, the 0.0812.
No. This K is your 1.38
Yeah, it was close.
times 10 to the negative 23rd joules per Kelvin. When you guys do each of these, looking at your units is very crucial, and I have a problem in here where you'll kind of see that if you don't take your units into account like very diligently, that it can easily screw you up just a little bit. So with this equation, omega is considered your number of microstates in a macro state. So with this example, we're going to use 2 dice. And on your dice, I'll just put macro. This is kind of in a way related to like statistics, as far as you're going to look at macro states as being your possible options and your micro states as being the likelihood that you'll get that option. So when you're rolling 2 dice, what are the range of numbers that you could possibly land on? 1 to 6, but you have 2 dice. Okay. So you could get, what's the lowest number you could get? Okay, 2. And the highest number being 12. So we're looking at a range from 2 to 12. So what's the number of possible macro states we could have? Yes. Does this make sense? Okay, so when you
2 to 12, and I have 11. But I have to read.
when you roll your dice and you have 2 dice, the number 1 isn't an option at that point. You're going to go from snake eyes up to 12. So that means that your values can be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So being a range from 2 to 12, you only have 11 options.
Okay.
So kind of in statistics, as you're looking at the different, possibilities, you have 11 options that you could pull out, say you're like pulling a number out of a hat or a marble out of a hat. You only have 11 options. So then when we look at our microstates, we're looking at the probability of choosing one of those options. So when we do this, choose a number from 2 to 12.
7.
Okay, we'll go with 4, and then we'll go to 7. Okay, so 4. The way that I like to write this out, because I'm a very visual person, is I kind of make it like a pedigree in a weird way. So, okay, so we're going to have a red dice and a blue dice. Red dice is going to be number 1, blue dice is going to be number 2. When we choose, or when we roll a 4, what options can we have between both of those dice?
We can have a 2 and a 2, but then we can flip it. We have 2 and a 2.
Okay, so
Right? Is that right? Are those the same thing?
2 and 2 are going to be the same, because if you roll it and you have a 2 and a 2, each dice
This is going to be.
is already 2.
So now take that logic on the side and apply it to 3 and 1.
Okay,
So we can have a red.
so we're going to have red dice is 1
Sure.
and blue dice is 3. But then we can also switch it and have red dice is 3, blue dice is 1. So then when we look at the number 4, how many microstates do we have? Okay. Is this equal to 3 over here, okay? Or do you need me to like write out 3 microstates? Okay. So then if we look at the number 7, what options do we have? Okay, so we'll do a 3 and 4, and then, yep, right away we'll do the 4 and the 3.
6 and a 1 and 1 and a 6. There's a lot of options.
And what else?
2 and 5. 5 and 2, 2 and 5.
Ah. That is not what I wanted. Two and 5. And we'll just go off this way. 5 and 2. Okay, so when we look at this, how many microstates do we have?
6.
Yes. Okay,
So we're kind of looking at a pattern.
right.
1 less than what it
So in this case of the dice, yes.
But not, we can't assume that for everything.
Right. Trying to think of. Okay, so this would get way more chaotic, but here's an example. If you have a hat and you have 5 different colors of marbles in there, and you're going to pull out 3 each time, what would you be looking at as your macro state, and what would you be looking at as your micro state?
Macro state would be the number of combinations you could get from 5 to 1.
So your macro state would be the possible options being your 5. You have 5 different colors.
And then 3, which would be your microstates.
It wouldn't just be 3.
The 3 possible combinations.
Right. So as you're doing this, this is why I'm saying it would get crazy, is because you would have to go through and you would know, okay, I could have 3 blues. I could have 3 reds. I could have 2 blues and a red. I could have 2 reds and a blue. Each of those would be a microstate. So that's why it would get a little chaotic on that larger scale. That's why.
It goes into factorials and stuff.
Yeah, but you guys aren't really going to deal with that aspect. That's more straight statistics based. But that's what I'm saying is there are different examples, but the dice is the easiest way to identify that. So it's not just that it's a pattern per se. With this case, it is just because of the sake that you have from the number 2 to 12, you're missing number 1. And so it just plays an impact. But does this make more sense? Okay, so if we were to say that we had a hat and we're going to put 5 different colors of marbles in there, and each time we're going to draw 3 marbles, what would you be looking at as your macro state, and what would you be looking at as your micro state?
So we would look for number of options. I guess it would be my macro state.
Yes. And then your microstates would be the different possibilities you have. So in straight physics sense, when we talked about those 4 variables being P, V, N, and T, the P, V, N, and T variables are our macro states. So we have those 4 macro states. And then within each of those, we have the options of changing position and momentum. So each of those possibilities within the 4 macro states is considered the microstate. If I need to reword that, I can.
Yeah, say it just one more time.
Okay, so your macrostates, you have 4 macrostates with this, being P, V, N, and T. So 4 macrostates. And then, so that's like the case of like 4 marbles in the hat. And then you can change your position and your momentum for each of those. So,
So we would bring it up to 8.
so say it's like you have 4 marbles in there and you're going to pull out 2 each time, because you could change your position on one and your momentum on another. Or you could change position on 2 of them. Or you could change momentum on 2 of them. That kind of thing. That you have, basically the biggest case to understand with this is you have so many different microstates. It's kind of insane. I think that's the best way to explain that. Any other questions on that? Okay. Okay, so we're going to jump into equations now. And we'll start with a more simple one. So I pulled this from Supplemental Homework 27. And it's problem number 1. I did do that.
If we have time, can we look at number 3?
Number 3 on which?
Supplemental homework 27.
Yes, if we have time. Let me see if I can find. Let me pull this up. So we're looking at Supplemental Homework 27, number 1. And actually, I already did number 3, so we can go through 3 as well.
I got the wrong answer, and I don't know.
It's a pretty quick one, so we'll get there. Okay. So do you guys all have what is the average kinetic energy in joules of hydrogen atoms on the 5,500 degrees Celsius surface of the sun? Okay. So where would you start with this? What equation would you want to use?
So first I saw average kinetic energy, so I go and I look for my average kinetic energy equation, which is it's something. Oh, there it is. 3 divided by 2 kV times T.
Okay, what?
3 divided by 2 kV times T.
Okay. So,
And then I went back to the back side of the equation sheet and I look up what kV is, which is the 1.38064 times 10 to the negative 23.
that's awesome that you guys have that on the back sheet. That's nice.
Joules divided by Kelvin. And then I changed my Celsius into not Celsius, into Kelvin.
Okay, perfect. That's the big piece to catch with this. So as you're looking at this, with this, we have to pay attention to our units. So when we note that, let me write this down, supplemental homework 27, number 1. Okay, so when we look at our Boltzmann's constant, we see that it's 1.38 times 10 to the negative 23rd joules per Kelvin.
That's KB.
Yes, that's KB. That's Boltzmann's constant. So when we note this, we want our actual, our results to be in joules, or our answer to be in joules. So we need to keep this Kelvin. In general, you're going to use most of these equations in Kelvin just because that's the natural SI unit that we use. So with this...
You said the only time you use Celsius is if you ask for Celsius.
Okay. Good to know. So with this, then we have the equation kinetic energy equals 3/2 kB T. And with that, we'll plug this in. And we have, what is 5,500 degrees Celsius to Kelvin? Yes. And then on here, I'll just write it out so that they have that. So we have 5,500 degrees Celsius plus 273 Kelvin. And what do you get for your kinetic energy?
Are you looking at the answer?
Yeah.
1.195 times 10 to the negative 19.
Okay.
Or 1.2.
Okay. So we have that. And we'll go down to number 3.
This is using that VRMS equation.
Yes. Which equation did I use?
January 17.
Okay. So, all right. So number 3, supplemental homework, 27, number 3. Okay, so I started out with the equation and derived myself there. I don't know how he wants it, if you guys can just go straight from that equation or whatnot.
I'm assuming that it's probably going to be straight from that equation.
Okay.
My guess
So-
is that if he puts one of these, it's going to be on one of those, that middle section.
Okay.
So you can just I'm assuming just plug it in.
I will show you what I did just in case that helps or you forget kind of thing. So we know that, let me pull up all of my equations. I don't know what I did with them. There we go. Okay, so we know that we need, in this sake, we need a mass, and we need like our velocity equation, and we need to relate that to our temperature. So I started out with the equation of 1/3 nm v squared equals nkt.
And you derived it from the equation sheet.
What?
You derived it from the equation sheet.
Yes. So the equation that I'm going to is also going to show you that derived. So I crossed out my ends on both sides.
Where did the 1/3
Did I write it down now? So this is, it's the PV equals 1/3 NMV squared. Let me see if it's on your sheet. It should be. Huh, maybe you guys don't have that equation. Okay, I'm not finding it on the equation sheet. I must have found it from the text instead then in the book. Okay, so there's this thing where PV equals 1/3 NM V squared. And then you also have PV equals NKT. And so these are the two bases for the equations that get you to your VRMS equation. So when you do this, you just set these sides equal to each other. And then you're going to multiply over your 3. So then you have NMV squared equals 3KT. Divide over M and square root. Okay, so that gets you your guys' equation for your VRMS. Sorry, I didn't realize you guys had that derived on there. So once this loads, maybe. Oh, right, there we go.
follow question.
Yeah.
On the, where they were going to give it to you, the RMS stands for what?
So that is your, I can't remember what the RMS actually stands for, but that was something I had to look at because I couldn't remember. I just knew that it was your velocity of, we're looking like the velocity of your particles.
Oh yeah. And the MP would be
The what?
MP, the MP equals the one underneath it.
Once again, I'd have to look that up. I just looked at the velocity in general.
Okay.
So I'll make a note of that. Okay. So with this, we'll use this equation then. So we have V RMS equals the square root of 3 kBT. And I'm not sure how he's always going to note it for you guys, but K just by itself is typically still that Boltzmann's constant. When they use the KB, it's just noting it for you. But in this sense, because you're doing just like thermodynamic stuff, your K is that. When you look at the final, that's when you're going to kind of need to know that a little bit better, or like look more in depth as far as like what kind of equation you're working with to be able to determine which K you're going to use. But that's why that, I mean, sometimes you'll see it and sometimes you won't. Okay, so then we have what to plug in.
So we have our temperature,
Okay,
correct? And it's
Yes.
already in Kelvin, so
correct.
that's at 2.00 times 10 to the negative, or 10 to the 13th, sorry.
2.0 times 10 to the 13th Kelvin.
Our KB, which is our 1 point something, and I can't remember.
1.38.
Times 10 to the negative 20.
And
And this
that's-
is where I got kind of lost on the M.
Okay, so we're going to scroll down a little bit to be able to have space to play around with our M. So
Just figured it out. I just thought
So when you look at your mass, we're talking about hydrogen atoms. And so we're discussing what would be the mass that you pull off the periodic table. It's your 1 point. I just kept it at the 008 just to keep it out for now. And what is that value?
Your molar mass.
Molar mass. Okay. So
And you divide that by
yep, Avogadro's number. And so this is your 6.02 times 10 to the, yes. I forgot my negative. And so, oh, whoops. Your molar mass is in kilograms per mole. And Avogadro's number is moles. Yes. So then when you get this, you have what value? What did you calculate? Anyone. It doesn't matter.
I have it, 1.67 times 10 to the negative 24.
To the negative 24, and what is this value in
Grams.
kilograms? Oh, I can't remember if I started off with kilograms. Oh, sorry, I converted. This is in grams per mole, but I did my conversion when I did it, and I just didn't keep units apparently.
Oh, okay.
So let me go back to this. So this is grams per mole. And then you have it in, right there. So then this is 6 times 10 to the negative 24th grams, but you want to get it to kilograms. So you're going to do your conversion of 1,000 grams to 1 kilogram. What?
SI unit.
So we always keep everything in kilograms. When we do like our mass, it's always going to be in kilograms, except for the off chance when you're doing like calories and you've already got your calories per gram, heat of vaporization, that kind of thing. But otherwise, every other time we're going to do kilograms. Okay, so we'll go back through that because I did it weird on my sheet. So to calculate our mass, we're going to pull our molar mass from the periodic table. And that for our hydrogen atoms is 1.008 grams per mole. And then Avogadro's number is 6.02 times 10 to the 23rd moles. And then with that, you get your 1.67 times 10 to the negative 24th grams. But you want this to be in kilograms. So then you're going to divide by 1,000 grams to convert it to kilograms. When I did it, for me, it's just easier to start out at, like, I did my 1.008 grams per mole and converted it to kilograms there, and then divided by Avogadro's number. For some odd reason, for me, it helps me to remember it better if I just do it right away. There we go. So then, pull up that number. And this gives us 1.67 times 10 to the negative 27 kilograms for our mass. And this is our little m. Okay, and then has anyone calculated this overall equation out yet? Otherwise I can.
7.14
You said what?
7.14 times 10 to the 8. 1, 2, 3, 4. Yep. 7.14.
And then when I did this, I got 7.04 times 10 to the 8th meters per second, but it's probably just differences in rounding. So, I mean, in that sense, with his like synthesis problems, you'll be able to like notice that little bit of a difference kind of thing. If you don't have the exact, you can always like work through it and not, simplify anything early on. But yeah, so that's kind of a way to show you how not only making note of your units, but also how to work with your mass and be aware of that. Then I have...
How much more stuff do you have?
I have 2 other problems. So one is going through, basically, it's the question that you had sent me about the cup of coffee. So we're working with like calories, and we're working with heat of vaporization, the MC delta T equation. And then I have a radiation emission equation. I don't know, I feel like he didn't go over that quite as much, but I did it just in case that's one of those things that he didn't cover quite as much and just might throw on there kind of thing. So the question that Emily sent me was from your guys' questions that you were doing at the end of class. And you said this was in the OneNote thing that we were looking at earlier.
Yeah. But we didn't get to this problem, that's why I wanted to go through it.
So is it... Yeah, it's the colorimetry problem. Do you guys have it pulled up, or do you need me to read it out or find it?
We have it.
Okay. Okay, so with this equation, how many grams of coffee must evaporate from 340 grams of coffee in a 95-gram glass cup to cool the coffee in the cup from 95 degrees to 45 degrees Celsius? So you notice that you have these thermal properties, noting that we're going to consider our coffee similar to water. And so we can utilize the average heat of vaporization being the 2340 kilojoules per kilogram, or 560 calories per gram. Because my mass of my coffee and my mass of my glass were all in grams, this is the one sense that I just decided to take less work and did the 560 calories per gram. You could, convert those both to kilograms and then use your kilojoules per kilogram heat of vaporization, but I just saved a couple extra steps. So when you do this, we know that the equation Q equals MC delta T involves our specific heat, and it involves our temperature and mass and whatnot. So with this, the heat that we're putting in, Q, we're going to utilize our Q equals heat of vaporization times mass. And I don't know if that's specifically on your sheet or if that's a derived equation that I've used. I'm not finding it yet. Oh, okay. So what they use, you can do it either way. So Q equals your heat of vaporization times M, or you can use, this is the same thing, is Q equals M times latent heat. That's what that L is there under your Q equals MC delta T. Okay, so with that,
Where is it on the sheet?
so if you go to General Thermodynamics, and off to the right column, in the middle, you find your Q equals MC delta T. Q is also equal to your mass times your latent heat, which is also the same thing as your heat of vaporization. So with that, you can set it up. Do you guys want me to stick with the HV, or do you want me to use the L and I can just note L of vaporization? L? Okay. So with this, I set it up so that I have my mass of, I'm going to put MV, because we're talking about, we want to find the mass that evaporates. And so I'm just going to put mass vapor. And then I have this multiplied by my L vaporization. And then this is set up equal to MC delta T.
So the whole purpose of changing Q into MV times LV is?
This is to relate, so we're looking at to identify how much mass evaporates. If we just solve for MC delta T equals Q, we have Q, we understand how much heat is put in, but we don't know how much of that mass was evaporated. So this is the way to kind of relate that. It's another one of those like where we manipulate the equations to be able to get the variables that we need. So with this, we need to take into account the mass and the specific heat of our coffee and also our cup. So we'll keep MV. What would be your LV? This is your latent heat of vaporization, or your...
So that would be the 560 calories?
Yes. 560 calories per gram. And then what do we need to do with our MC delta T?
First of all, we need to change our Celsius to Kelvin.
Yes.
But for the...
So actually in this case, we won't. If we were doing it with our kilojoules, or our kilograms per kilojoule, whichever, we would do it there. So with this, I'll
the specific heat capacity of the glass?
So actually with both of these, you can use your Celsius. So when you look at your little table, you're going to look at your specific heats because those are what you're going to use for your C. You have to pay attention to the units. So one is in joules per kilogram times degrees Celsius, and the other is in kilocalories per kilogram times degrees Celsius. So either way, using Kelvin would not work for us to be able to cancel those out. So we are going to keep it in Celsius, but there's something else that we have to do.
We need to change that 560 calories to kilocalories and kilograms.
I'll get to, so we'll stop there. So you can, which is totally fine. When you would change 560 calories per gram to kilocalories per kilogram, what would you be doing to convert that? You would multiply your calories by 1,000, and you would multiply your grams by 1,000, and so that would cancel out. So you'd be 1,000 over 1,000, which would just cancel each other out. So with that, you can totally do that. I skipped a step. Maybe don't do that on your synthesis problems for the sake that he's very particular about every little step. But I skipped that step, or you can note somehow, like, showing what that conversion would look like anyways. And I mean, if you were to put 560 calories per gram and convert it, it would still be 560 kilocalories per kilogram. So the value stays the same. So when you're doing this, you're going to have your delta T. So we have 95 degrees Celsius minus 45 degrees Celsius. The thing that I'm pointing at is that we need to include our mass and our specific heat of our coffee and our mass and our specific heat of our glass.
So you have to do both.
Yes. So I'm going to write this off to the side, and we're going to have to push it down because it's going to be a little bit lengthy. So we need, we'll use coffee, so MC, CC, plus we'll use glass, MG, CG. And then so what we're going to do here is we have MV, and I'll just change it for you. There. So then what is our delta T? Do you guys want me to keep it written out that way or simplify it? Okay. So we have 50 degrees Celsius multiplied by, we have The mass of our coffee is 340 grams. And this is multiplied by our specific heat of our water. So let me put a little bracket around this. So for our water, we're going to use 1.0 kcal per kilogram times degrees Celsius. And then we add this with our 95 grams multiplied by our 0.2 kcal per kilogram degree Celsius. Okay, does this all make sense?
Yes.
It makes sense to you guys?
Also write it down.
Okay, I'll take a moment.
Is your next problem long too?
No, the next problem is pretty short.
Okay, perfect.
Yeah, it's way shorter than this. This one has like a lot of different steps to it. The other one is very straightforward, plugging in, and then just one thing to really note with it.
Okay, question before we move on.
Okay.
Keeping it in Celsius
Because our specific heat is in Celsius.
okay.
When we look at this unit right here, this kcal per kilogram times degrees Celsius, that's in Celsius, so we're going to keep this in Celsius.
Okay.
If we were given a specific heat with Kelvin, then we would want to convert this to Kelvin. Basically, the biggest point is to keep track of your units and make sure that you're keeping consistent. And then however you do it, you can convert at the end if you need to, as long as you're keeping consistent. Okay, so with this, we can, to solve for our mass of that's evaporating, we can divide this over and solve.
Perfect. I got 32.05.
Yeah, I have 31.9, so it's the same.
That's
That's asking.
And that is in,
kilograms.
so yeah, at that point you can keep it in kilograms. Actually, okay, so here's the reason that it's in grams. Here's the reason that I had just converted my 560 kilogram to grams per cal, or cal per gram, and kept it that way is because I did not go through the process of converting my 340 grams and my 95 grams.
So just stay grams, not kilograms.
Yeah. So that's why I don't know how you want to do it. If you want to go through the process of converting every single thing, or if you just want to, I don't know. It's probably best to go through and convert your 340 grams to kilograms and your 95 grams to kilograms for his sake as he's grading. It was just one of those things that I noted that if my 560 kilocalories per kilogram would cancel out to just, or just to keep it there, that I just naturally mentally canceled out the kilocalories, kilograms across the board. Does that make sense why I did that? Okay. Okay, so this is 32 grams. So let me add another page. Okay, so the last one that I did was homework 30, number 4.
Supplemental.
I did actual homework. Okay. Okay. What do you guys have for your problem? Is it the consider the black roof on a night when the roof's temp is such and such?
Supplemental homework.
I'm on homework 30.
Homework 30, what number?
Number 4.
Yeah, the black.
Okay. So I know that the homeworks can vary on the values. So what I have is consider a 250 meter squared black roof. I'll write these down. When the roof's temperature is 27.5 degrees Celsius. And the surrounding temperature is 12.5 degrees Celsius. And we'll just put environment. The emissivity of the roof is 0.9.
We stopped doing class problems, and like half the class hasn't done their problem. So like, I have to, like, you know how you go up and you do work for a problem or something?
Oh, okay. Mm-hmm.
We're on number 3, but only 2 groups have been chosen.
Interesting.
So I don't know how you're gonna work it out because he's been talking a lot.
Hmm.
That was an extra. I did extra.
Okay, so what this is asking is at what net rate does heat radiate in kilowatts from the roof? So which equation are we going to use? Let me find.
It's yeah, C equals Q over temperature change.
Where are you looking?
General thermodynamics, where's the bottom? And it's the middle equation, the second column.
Yes, so the P radiation, that equation equals the heat of radiation over delta T. Is that what you're looking at?
Oh, I was looking at the one above it, but that makes more sense.
Okay, so your C is specific heat.
That's what I thought. I was like, that's
yeah.
not right, but that's the equation.
So the P radiation equation is the one that you'll want to use.
Okay.
And then
What's the difference between 3T and 1T?
okay. So how would you set this up? Do you know what those value or variables are?
Well, yes and no.
Okay. What can you tell me out of there?
The E is emissivity,
Okay.
and then the little letter caret thing. What is that? Sigma.
No, I can't remember. I don't remember anymore on that one, but that character, that Greek letter, that's your constant. I can't remember the name of this constant. If it's your Stefan Boltzmann.
Yeah, it's the 5.670.
Yep, times 10 to the negative 8th.
Yeah.
The units on that are watts per meter squared times Kelvin.
Okay, so we have to watch that.
Yes, that's something that you'll want to know.
We want kilowatts.
Correct.
then
And
the
let me see if it's
A
on here.
is area.
Yes,
And then the T's are the temperatures.
perfect.
And then, got it. Filled it.
Okay, so then you're going to plug everything in. When you do this, you're going to have your P radiation equals your 0.9 times your, here, let me write this actually out. Where'd it go? P radiation equals,
Do we have to convert? No, we don't. Because it's a change.
okay, so then,
Times 1,000?
so give me just a second, let me write this all out for you first. And then I'm just going to continue down. So we have, what is our T of our object?
27.5 to the 4.
So it's going to be 27.5 plus 273 to the 4th minus 12.5 plus 273 to the 4th. Does that make sense?
Yep.
Okay.
Then you just solve it through and then you got the answer.
Yep, solve it through, and I forgot to include my 250 meters squared.
For that watts, do you just convert that to kilowatts?
So you can do it with all of this, or you can do it after. So it kind of depends on how you want to do it. So you could do all of this
And then convert it to kilowatts.
divided by 1,000, because from watts to kilowatts you would divide by 1,000. Or you can actually calculate this through and then divide by 1,000. It's up to you. It's kind of, some people are different as far as like when they set up their equation, they just want to have everything ready to go, and some people need to break it down by steps. It's up to you. If you were to
Not a really small number. 0.0771.
give me just a sec. Calculate it through. Okay, so I got 21.4.
Oh, I forgot my 250.
Okay, that'll make a difference. So then when I did this, since I took out the divide by 1,000 there, I have 21,407 watts. That might just be where we, whatever, cut it off or whatnot. And then this would be in watts. So then we'd go 1,000 watts to 1 kilowatt. Okay, does that all make sense? Okay, so things that I will look at include verifying the little n versus the big N, the VRMS versus VMB, looking at what those are, and was there anything else?
The little and big N.
Little n, big N, and then
that number, number 4 on 14 or whatever.
oh yeah, I circled those. Number 4 and number 3 is what I have to look at the gamma. So I'll look at those, and then I'll send out a little email. I think that's it. Also, as you guys, like, after you take this exam, the next exam will be soon, kind of thing, but then your final will be, like, right after. So, as you're preparing for this, or is it all on the final? Okay, never mind. Sorry, I take it back. That was a huge mistake. So, you're going to have your final, but your final is in, like, 2 weeks now. So, as you start studying after Tuesday, and you're looking at everything, send me questions, because I'm trying to, now that I'm like, I only have 1 shift of preceptorship left, and it's only because we're trying to figure out if I can do a transport shift still or not, or if I need to do it on the unit that I was on already. So like my time is very free now, so I'm looking at the idea of maybe holding 3 separate exam review sessions, just to kind of be able to like, I'm looking at hopefully being able to do different questions each time as well, so that like I get a good inflow of like what you guys are really needing to focus on before the final, and then just like question ideas.
Cool.
So yeah, send me those
tutoring?
as what?
When's tutoring? Normal days?
Technically Monday and Wednesday.
Okay.
Since next week is basically your guys' last week. Is it your last week of classes? Sorry, I can't keep track anymore.
This week?
Next week.
Next
is our
week.
last week of class.
Oh, sugars. Wow.
So next week being your last week of classes, I'm hoping that maybe that during that week I could do 3 exam review sessions, but I'm trying to figure that out.
Sounds good. Thank you.
Yeah, of course. Have a good night, guys.